So hello and welcome to this CSRS 2021 talk on SAR analysis of the British Columbia Snowpack over the 2019-2020 winter season. I am Paul Bilcock. I am a PhD student at Sherbrooke University. So snow cover in mountainous regions of Canada has a great social and economic impact. It is the main contributor to freshwater resources. It attracts tourists for winter activities, and avalanches are a deadly hazard to recreationists and can severely damage human infrastructures such as railroads, highways, and buildings. The mountainous regions of Canada are extremely vast and they're hardly accessible, so that real-time knowledge of the alpine snowpack conditions is limited. Remote sensing could potentially help improving spatial coverage of snow conditions. However, the retrievals of snow state variables from space still remains difficult. Therefore, my research objective is to evaluate the potential of SAR satellites to retrieve snow state variables. I start with the presentation of the study site, then I present you the data I'm using for this study, and then I'll show you the methodology I put in place for this study. Afterwards, I present you the preliminary results, and I conclude the talk with a few take-home messages. For the study site, it's located in Glacier National Park in British Columbia, Canada. It is part of the Selkirk Range, which is itself part of the British Columbia Interior Range. It is characterized by a transitional snowpack, and my study site, which is circled in white in the map, is close to Mount Abbott and has a weather station which is located at 2,084 meters above sea level. Now, this picture, despite the fact that it's a beautiful picture, is showing my study site from afar. So it's located on this shoulder right here, and it's on in an alpine environment and has a general slope, so no trees. For the data I'm using, Mount Abbott Automatic Weather Station is measuring air temperature, wind speed and direction, relative humidity, precipitations, and snow height. The incoming long-wave and short-wave radiations are measured at Mount Fidelity Station, which is at 1900 meters above sea level, at the same aspect and roughly 10 kilometers west of Mount Abbott. For the Radarsat 2 data I'm using, I have 4 different time series at different beam angles, ranging from 21 degrees to 34 degrees. They are all in quad polarization, and 3 of them are in ascendant pass, and 1 is in descendant pass. For the Radarsat Constellation Mission data I have 2 time series, one in at 45 degrees of nominal incidence angle, and one at 36 degrees. They are both in ascendant pass. For the TerraSAR X data, I only have 1 beam mode, which is at 32 degrees of nominal incidence angle, and the polarization is dual pole, HH and VV polarization. For the methodology I put in place, so the general idea was to generate the best snowpack simulation I could for the season using the snowpack model. Then, using this snowpack simulation, I wanted to compute the simulated snowpack anisotropy using the model developed by Lance et al. In 2020. Then I processed the SAR products and extracted the relevant parameters, and at last I analyzed the SAR response with regards to snow model parameters. Snowpack is a snow physical model that takes into input weather data. Usually it's an automatic weather station data, and I used model data to fill in the gaps for when the automatic weather station was out of service. Then the model simulates mass and energy exchanges between the snowpack, the atmosphere, and the soil. The figure on the right is summarizing the different processes that are taken into account by the model. And then it outputs a column of snow layers, each layer describing its own microstructure state. There is also ongoing work in our lab focusing on fine-tuning the empirical model parametrization for our study site, focusing on, for instance, metamorphism biases and precipitation phase temperature. So this is the specific methodology for the first objective, the snowpack optimization. So I chose 4 variables: the wind scaling factor, which dictates the wind erosion effect and wind densification, the rain threshold temperature, the atmospheric stability model, and the density parametrization model algorithm of new snow. So all these different combinations gives us a total of 6,600 different parametrizations. And parallel to that, what I did is that I generated the best possible MED file using the weather station data at Abbott and Fidelity, and also the GEMLAB model. So I ran all of these 6,600 parametrizations, and to identify the best run, I did it by computing the Nash-Sutcliffe model efficiency coefficient between the model height of snow and the measured height of snow. I wish I had other criteria, such as different sensor temperatures at different depths in the snowpack to identify the best run, but it's a remote site, and we do the best with what we have, right? So snow anisotropy modeling. Anisotropy describes the orientation of the structure made by snow grains bonding to each other. There are two different processes driving snow anisotropy. The first one is temperature gradient metamorphism. It happens when there is a strong temperature gradient, and it's responsible for the development of vertical structures. Gravitational settling is the action of the grains falling on their own weight, and it's responsible for horizontal structure development. Anisotropy ranges between -2 and +2, -2 being unrealistic vertical structures, and +2 being unrealistic horizontal structure. When the anisotropy is equal to 0, the snow is perfectly isotropic. So this is the methodology I put in place for the SAR processing. And so for the polarimetric analysis, what I did is that I applied an adaptive Lie polarimetric filter for despeckling the image and doing some spatial averaging. And then I computed the coherency, copolar phase difference, and a few polarimetric discriminators. For the backscattered intensity analysis, I first converted the complex SAR image to backscattered intensity, and then I again applied an enhanced Lie filter to do some spatial averaging and despeckling. Now for the pixel extraction, what I noticed in preliminary work that is not shown is that ortho rectification of the image can severely alter the values that are present in the image, and therefore I chose to work only in SAR topology. So I built a shapefile with the different points for my different points of interest that I want to extract the data on, and I reprojected this WGS84 shapefile into each image specific topology. Therefore, I never did any mathematical resampling that allowed me to work into with the perfect pure SAR signal. Now for preliminary results. So this is the snowpack simulation for grain type. So this shows a rather homogeneous snowpack that started mostly as a faceted snowpack, which is pale blue, and gradually evolved into a round grain snowpack, which is pale pink. Light blue and light green are new precipitation. Light green and dark green are new precipitation grains, and red is melt forms. This is the liquid water content simulation. So liquid water is super important in remote sensing because water is a strong absorber. So it's absorbing the SAR signal very strongly. So here we can see that the first swelling appeared around the 10th of April. Now this is the anisotropy simulation for the snowpack. So red is horizontal structure and blue is vertical structure. So we can see that the snowpack started as a rather horizontal snowpack, and then vertical structures gradually developed starting in January, but the snowpack remained on average horizontal. It's also important to note that anisotropy values are ranging between -0.3 and 0.3, which shows that there is an anisotropy to the snowpack, but it's not highly anisotropic. So now the question that I want to address in this talk is snow really transparent at C-band? Because it's common to hear or read that snow is actually transparent at this frequency, but I want to check if it's actually the case in a deep alpine snowpack that I have in British Columbia. This figure is showing the evolution of the backscattered intensity with regards to snow properties. So on the lower part of the figure, each bar is showing in the snow plots is showing the density. Actually, each bar is a snow layer, and its width is density. Its color is the anisotropy, and the red line is showing the snow temperature. Now, this specific plot is showing the evolution of the backscattered intensity for the H-emitted polarizations at the FQ14 wide beam mode, which is at 34 degrees of incidence angle. So between the first two dates, we can see that there is a notable rise in snow depth, and that goes with a rise also in the average density of the snowpack. And this would create more volume interaction within the snowpack, and hence increase the backscattered intensity. And this is indeed what we have in the backscattered intensity plot. And we can also see that between the second and third date in the snowpack, there is the apparition of this hard density slab at near the surface, and this would increase the specular reflection in the snowpack, and hence diminish the backscattered intensity. And this is again what we see in the backscattered intensity plot. And we see the same behavior also with the VV-VH polarizations, with a slightly lower decrease in backscattered intensity between the second and third date. And this is, again, right according to Fresnel's law and reflectivity. Now this is the same plot, but for the FQ10 wide beam mode, so at a slightly lower incidence angle. Between the first two dates, there is not much change in the structure of the snowpack, and as a result, we don't see much change in the backscattered intensity. But between the second and third date, we can also see that this hard density slab that appeared is also there, but this time it's buried under some new snow. And as a result, we can see a slight decrease also in the backscattered intensity, again due to some specular reflection. We can see the same behavior in the VV-VH polarization, with a slightly lower drop again for the VV-VH polarization. Now this is the same plot for the FQ2 wide beam mode at 21 degrees of incidence. So this is way closer to nadir, and as a result we expect to have much less variability in the backscattered signal. And this is indeed what we have with a standard deviation between the three dates of around 1 decibel. And this is the same for the VV-VH polarization. We don't have much change in the backscattered intensity. Now I'd like to conclude this talk with a few take-home messages. So C-band is sensitive to snow cover in an alpine environment that is characterized by a deep snowpack. And I even push it to say that it's sensitive to strong density changes, for instance, And I also like to stress the point that working in SAR topology should be prioritized, especially in complex topography scenes where reprojecting can have a strong impact on the values that are extracted. Now, for future work, I'd like to expand this methodology to other alpine sites in the park, add the 2020-2021 data for the RCM and TSX satellites, and dig further on the polarimetric aspect of the signal, which is deeply impacted by the snowpack. Thank you very much for your attention, and if you have any questions or remarks, I'd be very happy to answer them. Thank you.